very much. This is a talk about Dasher, which is a piece of software for writing efficiently. It's based on information theory. And I'd like to start by just describing to you how the Dasher concept was born. I was sitting on the bus to Denver Airport with my friend Mike Lewicki 10 years ago now. And I got out my PDA, my Scion, which I still use. It's 14 years old now. And he looked at this thing in disgust, and he said, gee, that thing is so damn big. And that set us thinking, OK, why is this so damn big? Well, it's pretty clear. It's partly because of the size of the QWERTY keyboard that it has. So that set us thinking, how can we get rid of keyboards? How could we make a small writing system where the hardware that you interact with in order to write is perhaps just the size of a button on your lapel? So we were imagining, how would that work? If all you could do is touch something this big, how could you still write efficiently? And then we brainstormed a bit more, and we said, well, what if you didn't even have one touch object to touch? What if all you had was a head-mounted display, and maybe the display could track where you were looking? Then how could writing work? What would be a new way of doing the problem of writing with just a head-mounted display? Before I describe this solution we came up with, I'd like to review some alternative approaches to this problem of communicating on miniature handheld computers. There's essentially two metaphors for what writing is that people tend to use when they do things with computers. One metaphor about writing is a 200-year-old metaphor that says writing is pressing buttons. So if you want a miniature writing device, well, you just reduce the number of buttons and come up with some new system that still involves pressing buttons. Or perhaps you press multiple buttons at the same time. Another metaphor for what writing is a 10,000-year-old metaphor that says writing is scribbling with a stick. And so obviously, if you want to scribble on a small computer, you scribble in a small way using graffiti or unistrokes. And there are other sensible ideas like word completion and disambiguation. But these are all sticking with old ways of doing things. And I'm a bit of a fundamentalist at heart, and my attitude is let's throw out the old ways of doing things and let's get back to basics and try and come up with a completely new solution. And as a fundamentalist, I say, what's wrong with keyboards? Why are they a bad idea from the point of view of information theory? Well, keyboards are inefficient, I'd say, for two reasons. First, keyboards don't take advantage of the predictability of normal writing. If you're writing English, say, Shannon's estimated that the actual information content of English, if you're generating it, is about 1 bit per character. In contrast, if you've got a 64-key keyboard like this one here, and you press one of those 64 keys, each time you choose a key, you could have been conveying 6 bits of information, because 2 to the power 6 is 64. So there's a factor of 6 inefficiency there, because keyboards don't do language modeling. Of course, they were invented 200 years ago before we had such things as language models. The second reason why keyboards are inefficient is these things on the ends of my hands, we call them digits, but they're not actually digital devices, they're analogues. I've got 10 analogues, each one of them capable of high precision motor gestures and with a lot of fine control. And keyboards throw all that away. All you can do is detect whether a finger is up or down. And that's a big waste, again, of information content. It's been estimated that just a single finger can generate information at a rate of 14 bits per second. So here is the sort of fantasy, the theoretical motivation for what we're doing in the Dasher project. Let's imagine solving both these problems. We're somehow going to have a language model in there so that the bits that a human generates are turned into characters efficiently. And we're going to get as many bits as possible out of a single muscle, maybe just one finger. And if we could plug one finger generating bits at a rate of 14 bits per second into a language model with a conversion rate of 1 bit per character, you would then be writing at 14 characters per second, which would correspond to 170 words per minute with just one finger. So that's the sort of the goal, the ultimate benchmark we'd like to achieve in this project. And how do we go about this? Well, we steal from the best. And in information theory, they already know how to do text compression. And text compression is sort of an inverse process to writing. In text compression, you put in text, and out comes a bit string. And if it's a good compressor, the bit string is short. Writing, you make some sort of gesture, and out comes text. And an efficient writing system is a system where you make a brief gesture, and out comes lots of text. So there's a sort of analogy here that writing is perhaps a bit like back-to-front text compression. So let's steal from the very best. And the very best text compression method is an idea called arithmetic coding. In arithmetic coding, you put in text and a probabilistic model for the language that you're writing in. And out comes a binary string with a point in front of it, a binary point. And you think of this binary string as defining a real number somewhere between 0 and 1. And the more bits get added, the higher the precision to which the real number has been defined. And arithmetic coding, if you don't know about it, I can recommend a textbook that describes it. It's available free online. And probably by the end of this talk, you'll understand arithmetic coding anyway, because Dasher is just back-to-front arithmetic coding. You put in a gesture, which is a real-value gesture that's defining a real number to greater and greater precision. You use exactly the same probabilistic model as is used in state-of-the-art text compressors, and out comes text. So let me show you Dasher right now. And I'll write some sentences for you, and you maybe won't understand what's going on. Then I'll explain, and you'll understand. Can everyone see these characters okay? Would it be good if I made them a bit bigger? They okay? Great. Good. Okay, so let me write a sentence for you. I'll write, anything can be written. And I'm doing this with one finger here. Just moving the mouse around. Can be right, will be right. I want written. Yeah. Okay, so there, by moving my mouse on my touchpad, which is just this big, the same size as a lapel, I wrote a sentence. So, what was going on here? Well, here's a new metaphor for what writing is. Instead of writing is pressing buttons or writing with scribbling with a stick, writing is navigating. Navigating in the library of all possible books. And here, on a single one-dimensional shelf from A to Z, are all conceivable books. Not just all books, but all possible books, arranged in alphabetical order. So if I want to write hello there, I can navigate into the library of all possible books and find the book that contains exactly hello there. And by identifying that book, by navigating, I am writing. So to write hello there, we go into the H section of the library, within which are all the books from HA through HZ in alphabetical order. But what you'll notice, the smart thing we're doing is we're using our language model to allocate more shelf space to the probable characters. After an H, HA, HE, HI, HO are the most probable things that I'd be wanting to write. There is an HB section, an HC and HD in between the HA and HE locations on the shelf, but they're small because it's improbable that I would want to write something like HB. I go into the HE section. You may notice we have HEA through HEZ. This white area here, this is the space character. We put that at the end of our alphabet by convention in Dasher. So these are the books that begin he said, he was, and so forth. We want to write hello. We go into the HEL section, within which is a very big HELL section, which we've now entered. These are the books that begin with the word hell and a space, but we want to write hello, and there's a nice large O, which we can zoom into. And we can then get the space after that. Oh, incidentally, in passing, the next most probable character after space, in this context, hello, is W, because our language model has heard of yellow, and it thinks, well, maybe hello, yellow, maybe there is a word hello. That's the sort of thing that's going on in our language model's imagination. So we write THE. Now, I don't want hello the, so I don't want to end up inside this white box. I want to go into the R section, and that's how we write hello there. Okay. So how am I doing this steering? How am I moving around in this world? This is the tree of all books, if you like. Well, it's just like driving a car. We want it to be very simple for people to learn, and the idea is you point where you want to go. So if I want to write is, I point towards is. The distance from the center of the screen is determining the speed at which I'm moving. If I want to go up, I point up. If I want to go down, I point down. So let's write easy to write. And moving the mouse back into the center of the screen slows everything down again. If I want to back up out of the library, I can point left, and that's a way of undoing what I've recently written. And then I can go in and write it again. It's just like driving a car. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where you want to go. When you drive a car, you point where Your instructor may have taught you to hold the steering wheel like this, but we don't do that, do we? We hold it like this. And now when you want to go left, you point left, and when you want to go right, you point right. Okay? So it's just like driving a car. Now, some people say, oh, hang on, aren't you clicking on things and dragging? You know, isn't that the way we move things around on computers? You have to, well, it's just like driving a car. Do you drive a car like this? Click, drag, click, drag, click, drag. No. Moving things on a computer doesn't have to involve clicking and dragging, and in Dasher, emphatically, there's no clicking or dragging. You just point, and wherever you're pointing, if Dasher is running, then you're going in that direction. Okay? Now, some people say, oh, hang on, all this motion, I don't like it, it's making me queasy. Again, it's just like driving a car. If you go for a ride with Ralph Schumacher, and you're the passenger, he's the driver, who gets sick? The passengers, right? And Ralph is fine, because he's the driver and he can anticipate the motions and things that are going to happen because he's in control. And the same is true here. I'm the driver, you're the passengers. You're throwing up, but don't worry about me, I'm fine. And a fortunate feature of writing is normally it's a solo activity. You don't take other people along for a ride. So the fact that passengers don't like it very much doesn't actually matter. So I'll go slow for you. I'm going at 2 bits per second maximum here. I can normally go at 4 bits per second, so you're getting a factor of 2 compensation. Why is this a good idea? Let me hype up why Dasher is a great idea, and then I'll back it up with some science experiments if you want. The first reason Dasher is a good idea is we're getting many characters with a single gesture sometimes, in contrast to a regular keyboard where every character requires you to make at least one gesture if you're using a standard keyboard. Sometimes you may need to make 2 gestures for an uppercase character, for example. In contrast, in Dasher, if you've just written object, then with a little bit of swoosh you can get objection or objective or object-oriented programming. Now, when people see Dasher, they sometimes say, well, this is just a word completion system. What's the big deal? We've seen word completion systems for ages. You can get them on pocket PCs and so on. Yes, it looks like a word completion system, but there's an important difference. If you've got a pocket PC and you're pecking on the miniature keyboard, and you decide, I am going to use the word completion system, you have to make that decision. You have to stop pecking on the little keyboard, and you have to make a change of cognitive activity and go and look in the word completion area and interact with the device in a different way. Now you have to search for the word that you want, which is organized in a different way from the way a keyboard works. If it's not there, you have to say, damn it, make the change of mode. Where did I get up to in the word? Okay, let's keep on going. And those changes of mode have a cognitive cost. In Dasher, there are no modes. There is just using Dasher, which is interacting with the word completion system and writing with Dasher all at the same time. If the word completion system that is Dasher is doing a good job, you'll be writing fast. If it's not doing a good job, if the predictions are poor for what you are actually trying to do, you still write in exactly the same way. It's still writing with Dasher. You don't have to make any change of mode. You'll just be going a bit slower. A final reason why Dasher is a neat idea is inaccurate gestures can be compensated by later gestures. It's just like when we navigate. If you navigate from A to B, you're making a sequence of motor gestures to try and get you from A to B. And maybe one of the motor gestures you make isn't quite the motor gesture you exactly planned. What do you do then? Do you have to press some backspace key and undo that gesture? No. When we're navigating, you just keep on going and you modify your future motor gestures to make up for the error that you made a moment before. So you're perpetually correcting your errors and adding in more gestures to keep you on track to where you want to go. And this is true in Dasher too, that if I write, what should we write? Let's write in Dasher. And let's lose the D off the top of the screen. Whoa, come back. Let's lose Dasher off the bottom. Come back. So just by a little bit of extreme steering, I can make up for inaccurate earlier steering. Okay. Here's another benefit of the Dasher attitude. Having said we're going to base our thing in information theory, we instantly get a writing solution for every language on the planet. In contrast to something like graffiti, where you have to invent how do we do an A, how do we do a B, how do we do a C? Okay, let's do Russian. Okay, how do we do all the letters of Russian? That doesn't scale nicely. Dasher, straight away, we can use it in any language. Here is the hiragana alphabet, the phonetic alphabet of Japanese, which goes a, I, u, e, o, kaki, ku, ke, ko, and so on. And if I get back Dasha, I can tell it I want to write in hiragana. And now I can write hajime mashite, which means hello there, by going into ha. And ji me mashi, this would be mashita up here, but I want mashite, which comes after. So there's hajime mashite. And the only niggle in this particular demo is this particular issue of Ubuntu isn't correctly combining the she character with this diacritical mark here to give us a she. And hopefully that will be fixed in the next release of Ubuntu. Another reason why Dasha is a nice way of doing things is it doesn't require any special learning. I didn't have to learn what's the gesture for an A, what's the gesture for a B, and so on. I didn't have to go through a training period. All I have to do is navigate, though it does help to know the alphabetical order of the language that you're writing in. So Japanese, I can't write with handwriting at all. I definitely couldn't do it with a keyboard because I can't actually remember the whole alphabet. But because I know the order they go in, kakiku, keiko, and so on, I can actually write Japanese okay in Dasha. Going back hastily to English, let me illustrate how knowing the alphabetical order is sometimes essential. I'm going to write for you cream of mushroom soup, which I happen to know is not perfectly predicted by the language model. So we're going to the C, R, E, A, and let's, whoa, hold on a moment. I'm trying to write cream. Where's my cream? C, R, E, A. A beginner often makes a mistake here and says, I can't find cream, and he sort of puts the foot on the gas and hunts for cream by driving really fast, waiting for the cream to arrive. And that's not the way to do it. There is only one destination on this screen where you have written cream, and to get there, you must identify where it is and drive there. Keeping on going is a really bad idea. Beginners should be encouraged to slow down and wait and figure out where they want to go. Another beginner's mistake is to say, well, I want an M. I can see the A, so let's sort of wave the mouse near the A and then find an M on the screen, any M. Okay, oh, there's one down here. Quick, let's go there. But if we do that, what are we doing? We're going into the crime section of the library, because this is where you write C-R-I-M. The only way to write cream is you go into C-R-E-A, and inside that A box, you must find the letter M. And now I need to know alphabetical order. I can see the T. It's offering me create, creation, creature. I want something before T because I know alphabetical order. So I'll go above the T. I can tear across T land to get there. And here's cream. Cream of mushroom soup. OK. Here's a final benefit of the Dasha attitude. We can add extra characters to the alphabet, and we don't have to learn any new skills at all. So you might have noticed so far I've just been using lowercase English. And you might say, oh, he can't do general uppercase. Of course I can. No problem. We just change alphabet. So here's an alphabet that includes every character on a QWERTY keyboard, and then some. It's got a bunch of other Unicode characters in there as well. And we put all the uppercase characters in a yellow box. So now let's write hello there. I go into the H, and then into the E. And what you'll notice now is the way the screen looks is just like the way it looked when I was writing in lowercase English only. So I'm in the middle of a word, and all you can really see coming up are lowercase characters. So the fact that I've got 3 times as many characters available to me, a whole load of punctuation characters and uppercase characters, it isn't slowing me down. So I've got 3 times as many options in the tree, but the language model is highlighting all the probable characters, which are the lowercase characters. So we can add more characters, and it doesn't slow us down. If I write hello there and terminate the sentence with a full stop, then what do we find? Well, now we get a nice big white box saying space expected after the full stop, the period, and a big yellow box saying uppercase characters are highly predicted in this context. So that's great. It's making it very easy to begin the next sentence with an uppercase character. If, however, I don't want to start the next one with an uppercase character, I can go into the space and go and find lowercase characters. And maybe the next thing I want to write, I don't know why I would want to do this, is Microsoft. So I go, and I got the lowercase m. And I write Microsoft, which takes a long time to write because it's an improbable string. It's never seen this before. And what you'll notice is when I have put in that extra effort to get that difficult to find lowercase m, this smart software gives me the word Microsoft with a lowercase m. It doesn't convert it back to uppercase. And my feeling is that's the way that smart software ought to work. How are we doing the predictions? We're using, as I said, the state-of-the-art in general purpose text compressors. It's a model called PPM, prediction by partial match. It's embarrassingly simple how this works. It just looks at the last 5 characters that have been written and uses that as a context to predict the next character. So it's based entirely on the 6-gram statistics of the language. PPM can compress English down to about 2 bits per character. So in principle, if we could make a better language model with all human knowledge built into it, and if Shannon's right that English is really about 1 bit per character, Dasher should be able to go twice as fast. And that's something we're still working on, trying to make better language models. We chose PPM because it's fast, it's adaptive, and it works with any language. It can learn all the time, so everything that we're writing here is being learned, and you can train it on your own writing style. This screenshot here shows what happens if you train it on just 100 favorite phrases. Let's say you're a severely disabled person, and what you want to be able to say are just things like, please turn up the music, or please give me some water. Here I've trained it on those 100 favorite sentences, and you can see now it looks like it's just the tree of all my favorite sentences. And that's happening even though we're using this language model that only knows about 6 grams. It ends up emulating the tree of sentences pretty well. OK, so I've hyped it up. Let me now give you a bit of data on how well Dasher works. These experiments were done by David Ward with volunteers from the astrophysics group in the University of Cambridge. He gave them dictation from Jane Austen's Emma, having trained the language model in the style of Jane Austen's Emma by training it on 90% of Jane Austen's Emma and then testing on parts from the other fragment. And they learned to use Dasher over a period of 1 hour in 12 5-minute sessions. And these sessions were mixed up with keyboard dictation sessions to check that it wasn't just that they were getting good at taking dictation. And David measured their writing speed and the word error rate. The writing speed is shown up here. Bottom of the class started out at about 5 words per minute, and after an hour of practice was still bottom of the class and going at about 10 words per minute. Top of the class started immediately in the first 5 minutes, going at 12 words per minute, and was up above 25 words per minute after 1 hour of practice. So this is a very steep learning curve. We're not aware of any writing system that has a learning curve steeper than this. Meanwhile, on the keyboard, they were all going along at something like 50 words per minute. This was something they'd already been doing for perhaps 18 years of their life. The error rate, I'd love to be able to say that the error rate with Dasher dropped to 0. That's what I really believe is the case when ordinary people use Dasher to write their own writing. The problem here was that many of these astrophysicists unfortunately didn't know how to spell Jane Austen's flowery prose, and so there were spelling errors coming through for some of them here at the end. Meanwhile, on the keyboard, as we know, your favorite key is the backspace key because people do make a lot of spelling mistakes by mistyping if they're trying to write fast. Now, at this point, people might say, I don't like Dasher because it requires visual attention. I like to be able to look at other things while I'm typing. OK, I'm not trying to force everyone to use Dasher. And this is the way that a predictive system has to be. If it's a predictive system, we've somehow got to get the predictions of our language model into your head. And that's going to be either auditory or visual, and we're using the visual channel. So yes, we require visual attention. It's just like driving a car. Oh, I hate driving a car. I have to look at the road all the time. I'd much rather not look at the road. And just like with a car, we can actually turn this to our advantage. Because with a car, you're looking where you're going all the time. So actually, you don't need the steering wheel. You can just look where you want to go, and we can have a gaze tracker take you there. And we can do exactly the same with Dasher, and it works even better than that car idea. So here's a gaze tracker that we bought from a company in Arizona. Infrared camera, 2 infrared lights, gets an image like this, figures out where your eye's looking, puts the mouse on the screen in that location. And here's a movie of me taking some dictation using this iTech system. And the dictator says, no objection was raised on the father's side. This is the image of my eye, and this is me writing at about 3.7 bits per second, completely hands-free, and it's a lot of fun. It's just like It's just like navigating. You just look where you want to go, and you go there. The young man was treated liberally. Okay, so David Ward and I published these results a while back now. And we compared using Dasher with a gaze tracker with the cruelest form of torture known to man, which is an on-screen keyboard, which is the standard thing that people using gaze trackers are forced to use if they want to write. So an on-screen keyboard, you stare at the keys one at a time. You have to stare for the right duration, so it goes blip, but not too long, so you get 2 blips. And you can have word completions if you want. You can have a word completion area. So you blip, 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 then you look in the word completion area. But you had better look really quick to try and find your word, because if you look too slowly, you'll select a word you didn't actually want. It's hell using an on-screen keyboard. The fastest that you can go is about 15 words per minute. And that's for expert people very familiar with QWERTY keyboards. And the error rate you'd be making at that sort of speed is quite likely 1/5 of the words misspelled. Meanwhile, with Dasher, expert users of Dasher, already familiar with Dasher, started out at 10 or 15 words per minute, and we're up at about 25 words per minute after an hour of practice. And the error rate was essentially 0 for the expert users. We've since modified Dasher to work especially well with gaze trackers. The previous results were just using our off-the-shelf Dasher designed for use with a mouse. We made an eye tracking mode, and the speed is now up almost to 30 words per minute. And this is in use by real people. Here's a chap called John Law who's got motor neuron disease. He's using the same piece of hardware with Dasher, and I found this photo on the internet. And you might wonder, hang on, how's starting and stopping working? I told you I'm not clicking, I'm not dragging, but I am pressing a button at the moment to start and stop Dasher. Well, there are other ways of starting and stopping. One idea is to have a central circle which you look at to make a start or stop event happen, and that's something we're shipping in the current version of Dasher. And I'll show you that with the next demo, which is a cheaper option for hands-free writing. At the moment, gaze trackers cost $20,000. But a much cheaper device you can get is a head tracker. So you can get one from Natural Point or from Origin Instruments, the Head Mouse Extreme. And I'm going to use the shiny dot hat of Natural Point, which has a shiny dot on the front, like a bicycle reflector. And I'm going to use it with the Head Mouse Extreme, which works with any USB port. And you can see I'm now able to move the mouse up and down on the screen with my head. OK, so let's get the mouse circle option available. And let's start a fresh sentence. I'm happy to take suggestions for what to write.
Well, I'm feeling lucky.
OK, good one. Oops. I am feeling lucky. OK, and I'll stop by going and looking in the circle, like that. OK, so that's starting and stopping without pressing any buttons at all. And something you may have noticed was I wasn't pointing very accurately there. Even though Dasher has very small objects on the screen, people might say, oh, I can't possibly use that. I can't point that accurately. You don't need to point accurately. I was wobbling all over the place, but nevertheless, I got to my destination, just like a wobbly car driver. And so high precision is not required by Dasher, in contrast to some other software I've come across that has icons about this big that you're expected to click on to get things to happen. And those are very difficult for disabled users to use. And maybe the proof of the pudding is to actually do a study on a real user. And Mick Donegan at the ACE Centre in Oxford made a study of a young man called Paul who has cerebral palsy, has been in a wheelchair all his life, has great difficulty controlling his muscles, can't talk, and who has been using, until Mick introduced him to Dasher, he was using an on-screen keyboard with a head mouse for all his communication. And here's a video of Paul using Dasher after, I think, a month or so of trying it out. So this is Paul's head here, moving around. And you can see the rate at which he's moving in Dasher is very similar to the rate I've been demonstrating it to you today. And Mick interviewed Paul and asked him what he thought about Dasher. And he said, in contrast to the on-screen keyboard, which requires tiring head movements, it requires movements over quite a large range, and the movements have to be quite precise and held for a particular duration. Dasher needs less head movement over a smaller part of the screen, and there isn't any need to click or dwell at particular times, and he thinks he can write about 4 times quicker with Dasher, and finally he makes fewer spelling mistakes. And the last piece of good news was he used Dasher to write his final thesis at Aston University and graduated in 2004 with a bachelor's degree. The Dasher concept is very versatile. It doesn't just work with a mouse and a head tracker. It works beautifully with touch screens. Here's a movie of David Ward writing on a Pocket PC. This is something he did in 2001. He's left-handed, so his hand doesn't get in the way of the stuff coming in from the right. We're working on a version for right-handed people at the moment. So one of our mottos in the Dasher project is write with any muscle. And so far I've shown you mouse, gaze tracker, touchscreen, and head mouse. And next, just to illustrate this philosophy, I want to demonstrate to you my breath mouse, which Ryan Adams and I made. Okay, so now if I breathe in and out, the mouse is going up and down on the screen. That's a one-dimensional muscle, if you like, a one-dimensional control. So how can we steer? How can we navigate? How can we drive a car with just one dimension? Up till now, I've been using 2 dimensions to steer Dasher. Well, we don't need 2 dimensions because we can map this one dimension around this red clock, if you like. So breathing out takes me down or unzooms me on this side, and then going around the clock, I can go forwards, or I can go back in the other direction. So let's show you that right now. I'll switch over to one-dimensional mode. Okay, I think we're ready to roll. So let's write, thank you for inviting me to Google. Okay, so I'm not sure if this is a serious option for any real user, but it does illustrate the philosophy that if you can move any muscle, we can get a piece of hardware and we can have that one muscle drive Dasher and make efficient use of the gestures that you can make with that muscle. And the writing speed with this particular piece of hardware, some beginners struggled and started out at 2 words per minute and got up to about 6 words per minute. And meanwhile, an expert, no prizes for guessing who, started out at 11 words per minute and got up to 15 words per minute after an hour of practice with this new device. And this one-dimensional control, I think, would be absolutely beautiful for handheld devices. I've been trying to persuade Samsung and Nokia that they should have a phone with a tilt control where you use this 1 degree of freedom to write your text messages. And this would be great for cool people who like to write one-handed text, and it would be great for disabled people who can't use mobile phones at present, many of them. I think it would go nicely, say, with the Nokia lipstick phone, which just has a continuous one-dimensional controller on it and no keypad. We have various other ways of using Dasher for people with different abilities. And what about people who can't actually control one muscle in a continuous fashion? Going back to buttons, if someone really can only press 1 or 2 or 3 or 4 buttons, what can we do for them? Well, again, we can use information theory, and we can say, what's the best way to get information content out of the ability to press 2 buttons? And if all you can do is choose between 2 buttons, a very sensible thing to do is to say, well, let's not label those buttons with letters of the alphabet. Let's have them correspond to navigation actions. So we can have a button for up and a button for down. And that's the optimal way to use 2 buttons if you can press each of them with equal ease in the same amount of time. I'll skip over the demo of that and move on to another way of using 2 buttons. This is assuming that what you're doing is choosing between 2 buttons. If you can actually choose when to press one of those 2 buttons, there's additional information content in the timing of the pressing, not only the choice, but the timing. And we've made a version of Dasher that we call dynamic 2-button mode that exploits this in, we think, the best way that is possible. This was an idea of Radford Neal's. And the idea is that the car drives steadily forward, and you press a button to indicate when your destination is falling off the screen to the left or to the right, or rather, up or down. And which button you're pressing indicates which side of the screen you want to recenter the view on. So let's get 2-button dynamic mode. And now I can write another sentence for you. Any suggestions? OK. There are no suggestions, so I'll write that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That was 13 presses of a switch. And how many characters are written there? I think more than 13. So we're getting a very good conversion rate of gestures into characters. And was I having to press really fast, like Morse code, to write at that speed? No, I was only pressing about once per second, I think. So I think this could be great, again, for mobile phones. One-handed entry using just 2 buttons like this, very comfortable rather than having your thumb going in awkward angles. Just 2 buttons on a mobile phone. I'd love to persuade a manufacturer to get this software onto a phone. And it would be great for disabled people, again, because someone who can press just 2 switches with their head would have an option of writing text messages on a mobile. OK. I'll skip over the results. 20 words per minute is the sort of speed that you can get up to with just two buttons. So who is Dasher for? Well, the Dasher program that's available at the moment, I think we're especially focusing on the group of people with special needs. We think it would be great for people with miniature computers as well. It's working on the Pocket PC and on this Nokia Internet tablet. We think there's a lot of potential there for people with portable computers. Also, people who want to write in languages that are not supported by the keyboard they are sitting at. So here's a screenshot of International Phonetic Alphabet being written. Maybe Dasher could be useful in education and in language learning also. I'd like to close by showing you a few directions that the Dasher team are going in now. One of the activities is using Dasher with other sources of information. For example, if you can talk and move one muscle, what can we do? Well, we have an idea called Speech Dasher. And this is an example of a whole class of problems where you have other sources of information. So here, speech is the other source. And speech recognizers. Do many people use speech recognizers to write on their computer? I think not. They advertise them with phrases like, you talk, it types. But why is the nice gentleman smiling so much? The real slogan is, you talk, it types, you laugh, because it makes so many mistakes. And I think it's well established that whereas raw dictation itself could go at something like 140 words per minute, all the correcting of errors that you have to do with real recognizers, even in good conditions with a good quality microphone, the correction process slows you down so that you end up writing at about 14 words per minute. That's if you're using a mouse and keyboard to handle the corrections. If you do the corrections by voice alone, you go even slower. And just to remind you of that, here is a movie that Keith Burton made on a speech recognition system.
A hibernating skunk, curled up in his deep den, uncurls himself
and ventures forth to prowl the world.
Select Dan.
He wants den.
Den. Select Dan.
He wants den.
Spell that. D-E-N. Select on curls.
He wants uncurls.
Scratch that. Select on curls. Uncurls. Select Anna curls. Spell that. U-N-C-U-R-L-S. Select uncurls. Scratch that. Scratch that. Spell it. Scratch that. Uncurls. Select on curls.
He wants uncurls.
Select on. Scratch that. Select on. Scratch that. UN. Scratch that. UNCURLS. Scratch that. Uncurls. On current was. Scratch that. Scratch that. Uncurls. Select Anna curls. Spell that. UNCURLS. Select and.
So he's still not done. And the question is, can we do better than this? And I believe that with a Dasher speech hybrid, we can, because we have a new way of entering information, a new way of using navigation. And here's a screenshot of what it looks like. Imagine you have just said, I follow curious to deduce his state of mind. And the speech recognizer says, well, I'm not sure if he said curious or curries or furious. And so on the screen, these alternatives are displayed in the Dasher way, in alphabetical order. And so here's Keith's first prototype. He's made several. I'll just show you a video of his first one, where he says the same sentence.
The hibernating skunk, curled up in his deep den, uncurls himself and ventures forth to prowl the world.
A language model is deduced from the output of the speech recognizer. It's rendered on screen in alphabetical order, and now he goes and chooses what he actually wanted. The hibernating skunk curled up in his deep den. Notice how fast all that was. That was faster than speaking speed, perhaps. Uncurls himself. Now this takes some time, because the recognizer didn't get uncurls. But now he's got it, and he keeps on going. Uncurls himself. And ventures forth to prowl the world. So Keith is still working on this. He's finishing his PhD at the moment. We could use the same principle as part of a translation system to help someone clean up the errors made by an automatic translation system. We can use the Dasher concept where the grammar is constrained, so that instead of being able to write any sentence at all, you should only be able to write something that obeys some grammatical rules. For example, search. If you want to search for a string in a document, it's stupid to allow the user to type in strings that don't exist. So here's search Dasher that is a way of entering strings that exist in the document. So here Phil writes THE, and we're highlighting on the left the occurrences in the document of that string. We can supply rudimentary editing using the Dasher metaphor, so you can go into nodes in a menu hierarchy that offer you the opportunity to move the cursor around, to delete characters, and so forth. It's a bit like VI hitting the escape key to get into this alternative tree of actions. In fact, you can access not only those elementary editing actions, but all of the menus, in principle, of all the applications running on your computer can be accessed from within Dasher. We're not shipping this version because it might cause problems and crashes and so forth, but we have made a prototype where you can pull down your menu of your Abbey Word and select bold formatting and write text in Dasher that comes out. And this is a real screenshot of this process, controlling the computer entirely through Dasher. And we call this a user-friendly alternative to the wheelchair alley of death, which is the sequence of pull-down menus, which, again, are very difficult for a disabled person to actually control with, say, a head mouse. To wrap up, I'd like to emphasize that we can use Dasher in any language, and I'd like to end by showing you screenshots of Chinese Dasher and Japanese Dasher, which we're just finalizing at the moment. I understand Google might be interested in Chinese text entry alternatives. So here's Danish, Finnish, my 100 favorite phrases, Swedish, Polish, Arabic, Hebrew, going in the opposite direction, incidentally. Persian, Bengali, Urdu, Tamil, International Phonetic Alphabet. Here's a semantic alphabet for people with cognitive impairment, LaTeX, C. Korean works beautifully. Korean has 11,000 characters, each built out of 2 or 3 elementary letters, which are consonants and vowels, and we can render that in Dasher, and it just works straight out of the box. No difficulty at all, at least in Linux, where these things work fine. Chinese, 7,000 odd characters are in Chinese, and the way we're handling Chinese, we need a new language model here to cope with such a big character set. And the way we're working in Chinese is you enter the sentence you want to write in pinyin, which is the phonetic alphabet of Chinese. At the moment, we're not including the tone marks, but I'm sure it will work even better if we have the tone marks included in this string, and we can do that. Then you enter a special character, this one here. That means, OK, I'm done. I want to convert this. Then we get a language model from a piece of free software that comes up with hypotheses about how to turn this into Chinese characters. And here is that tree of all possible strings of Chinese characters. And now the user zooms through that sequence and gobbles up what he actually wanted to say. And there he's done. And now he comes out, and he's back into pinyin to write the next sentence. We're doing exactly the same in Japanese. Here's a screenshot of Japanese done one way. Here you enter an entire sentence in hiragana, then enter the special character, then choose the Chinese sequence that you wanted, all within Dasher. The other way of doing things, rather than doing a whole sentence at a time, is to convert after every word, and I think that's going to be better for users. So here's today's version, where this is a word, I think that says watashi no, and this is then converted to watashi no here. And then here's the next word and the conversion to the next string. So this is where we're going with Japanese Dasher, and I hope we'll have that out of the door within another month or 2. So we'd be delighted if people world over would get involved in Dasher. It's free software. It's available on quite a few platforms, Linux, Windows, Mac OS, Pocket PC. We'd love volunteers to get involved in porting it to other platforms like the Palm Pilot. And we do have a Java version working in your browser as well. And so I hope this might be useful to people at Google. Thank you very much for listening.
The width, or rather the height of the box is proportionate to the probability. Have you tried kind of changing that scaling in some way that minimizes the average time per character?
OK, the question is, how are the sizes of the boxes being determined? We've got a probability model that says what the probability of each character is. How do we actually use that? And is it optimal in terms of writing speed? So what we're doing is the vertical height of each box is proportional to the probability. So we chop up each box in proportional to the conditional probabilities of those characters. And that is the optimal way in terms of getting the best possible writing speed if we assume that the user drives at a steady rate. So if they can sustain a constant rate of zooming. So for example, 4 factors of 2 of zooming every second would be 4 bits per second. Yeah?
So is there any plan for people with vision problems, like blind, or people who have like weak muscles and stuff like that?
Right. So the question is, what about Dasher for blind people? And for several years, when people asked that question, I said, come off it. Dasher's intensely visual. There's no way I could make a version of Dasher for blind people. But after enough people asked this question, I did actually come up with an idea. And so we have a version of Dasher that I've made a prototype of called VI Dasher, for visually impaired Dasher. And I can show you just a screenshot of the concept. We're assuming here that someone is not only visually impaired, but that they have severe motor difficulties as well, so they can't just use a keyboard. So here I'm assuming that they can press 2 buttons, an up button or a down button. And the idea is to give them the set of all words in a language in alphabetical order in a tree. And you can then use one switch to go alphabetically before the word that's being offered to you, and another switch to go alphabetically after And maybe a double press or a long press is a way of selecting the word that's being offered. And then you can optimize this tree to maximize the information rate. Why is this visually impaired? Well, we don't have to show the words. We can speak just the single divider word, which is telling you where you are in the library at the moment. So it'll say to you, my, and then if you want to write hello, you say, oh, before. And then it says for, and you say, OK, after. So we do have an option. We don't have any users using this, but that's the idea.
How do you decide what colors to use?
The question is, what's going on with the colors? And in some languages, there are very natural ways of associating colors with characters or symbols that have different meanings. So in Japanese, for example, I couldn't survive in Dasha without the color coding that goes a, i, u, e, o, kakiku, keko in orange, sasisu, se, so in yellow, and so forth. In English, there isn't such a natural grouping of characters. We could color vowels and consonants differently in principle, but we don't because we don't think it really helps. So the colors we're using in English at the moment are a yellow box surrounds all uppercase characters, a red box surrounds numerals, a green box surrounds punctuation, and the punctuation characters themselves are colored in a systematic way to make it easy to find quote-like characters or period-like characters. And the letters of the alphabet themselves are just randomly colored with 6 or so colors to give you a feeling of navigation in a colorful world, perhaps slightly Google-flavored color scheme. If you don't like that color scheme, we've got lots of options. So you can just say, I want the appearance to be, for example, milder. And here is the mild look, which isn't so googly in appearance. It's much more soft blue and green shades there. So any ideas for how to improve the color scheme are welcome, and it's all open source XML files, so it's very easy to redefine the color scheme if you have an idea you'd like to try. Yeah, Jeremy.
Can you imagine 1 million people using Dasher in the next, say, decade, and how would that happen?
Jeremy's question is, can I imagine 1 million people using Dasher within a decade? I definitely can, and I can see that happening in 2 ways, 3 ways, 3 categories of user. There's all people with mobile phones who want to do their mobile phone business one-handed, text messaging especially. Maybe they're holding a beer in the other hand. So there's that community, and easily that could be 1 million users. There's all the disabled people who can't use a keyboard. And then the third category is, where was I going? Yeah, so I think in Japanese and Chinese users, I think there could be a big win for them. I've seen Japanese people using the Roman keyboard, which is the default keyboard, and it's a struggle for them. And so I think there could be a big win there. I think there's some other group of users that I've forgotten as well, but you can probably figure it out. OK, thank you very much.